Good afternoon, Internet. I am Matt Buyak, and in this video, we'll be taking a look at the 36th problem from the Project Euler problem archive. Now, this problem asks us to find the sum of numbers less than 1 million, which are a palindrome both in base 10 and base 2. That is, when written as a decimal number and when written as a binary number. I'm actually going to show you 3 different ways of solving this problem. We'll start off with a basic solution, and then I'll show you 2 different ways that we can optimize our solution. So let's get into it. As usual, we will copy our template directory to make our problem directory, and open our main.cpp. So the first solution that we're going to implement is going to be very strings oriented. We're just going to try each number from 1 to a million, represent it as a string in both binary and decimal, and then we'll check to see if each string is a palindrome by copying it, reversing it, and comparing it to itself. Now, we already have code to write a number as a string in decimal. You can use either sprintf or the toString method included with the STL. Let me actually just bring that up real quick since we will be using that. This function here, toString, but there is no function for in the standard template library for writing a number as a binary string. And so we'll have to implement that ourselves. All right, so let's start off by writing our function is palindrome. So this is going to take, as I mentioned, a string. Let's make it constant. And it's just going to return true if our string is a palindrome. So first we'll make a copy. We'll say string copy is equal to string. And then we'll say std reverse copy.begin copy.end. So this function here is not specific to strings. You can use this on any container with an ordered range that has, these are iterators to the beginning and end of the range that we want to reverse. In our case, the entire string. And we'll need to include algorithm and string. And then we'll just return copy equals string. That is, if after reversing copy, it's still the same as string, that means we must have a palindrome. Okay, and as I mentioned, we're going to need to be able to write our numbers as a string in as a binary representation, and we'll need to write our own function for doing that. So let's say std string to binary string. We'll take a 32-bit integer, call it n. Now you may remember the algorithm for writing a number in a particular base is just to take that number and repeatedly divide by the base and look at the remainders that that gives us. Unfortunately, this gives us the digits in the opposite order that we would want. That is, if we divide by 2 and take the remainder to get the first bit, then that will be the least significant bit rather than the most significant bit. And when we're writing these to a string, we need to write the most significant bit first. So what we'll do is we'll write the string backwards, and then again we'll reverse it to get the string in the order that we want. So we'll just say while n, we'll need a string here. Say while n, we'll do ret.pushback. So there is also a method append in the string class, but it's a little bit weird because it takes a number of characters, and we only want to push one character, and so it's a little bit more precise to use pushback rather than append. Okay, so we're just going to say 0 plus, and then we need to divide by 2 and take the remainder to get that first bit. But it's actually more efficient to use bitwise, logical bitwise, excuse me, those are two different things, to use bitwise operators instead of division. We could do n, divided by, this is the modulus operator, we'll divide by 2 and take the remainder. But it's actually more efficient and equivalent to do this. Okay, and then we'll say n shift right by 1. Again, we could say divided by equals 2, like that. That would be equivalent, but it's more efficient to do it this way. And depending on your compiler, it may be smart enough to do this optimization for us, but we'll just put this in here just to be sure. Okay, so now we have our string, but it's backwards, so we just say reverse ret.begin, ret.end, and return ret. Now you might be concerned that we're returning this string that is an object rather than, say, an integer. This seems like it would be really expensive. You're copying memory around. But there's actually an optimization that's part of the spec in C++, where if you return an object essentially by value like this, what actually happens under the hood is that the memory for that object will be created on the stack by the caller, and then that address will be passed to this function as an argument, and the object will be constructed into that location. And so it avoids this extra copy that seems like it might take place on return. Okay, so now we have most of the code that we need. We'll, rather than writing our solution directly into main, I'm going to make a little side function here. We'll just call it solver1. And this is just so that we can easily switch back and forth between different implementations. Later, we're going to be timing our solutions to see which are more efficient. And it's easier to switch between solutions if we put them in a separate function like this. All right, so we're going to go from n is 1 to less than 1,000,000. And then we'll say std string decimal equals std to string n. And then we'll say std : binary, string binary is going to be equal to 2 binary string. This is the function that we just wrote. We'll need a variable sum initialized to 0. And we'll say if is palindrome decimal and is palindrome binary sum plus equals n. And just for our own curiosity / sanity check, we're going to do printf. We'll say %s in decimal is equal to %s in binary. And we'll say, and then we'll print out the decimal string and the binary string. And then at the end, we'll print out our actual answer, which is going to be the sum. And down here, we'll call solver 1. All right. Seems to be something that we've done that it does not like. Yes. That's right. These are not C strings. These are STL strings. So you have to do a .cster to get the C style string out of that. Okay. We're going to do time solver. Okay. So looks like it took about half a second, and we can see our result there. As a quick sanity check, we can look up and down this list and see that they do appear to all be palindromes. And for the smaller values that we might be familiar with, the binary representation, it seems to have done the conversion correctly. Okay. So now we can take a look and see if we've actually got the right answer. Going back to the archive here, we can see indeed this matches our solution. If I just move the window up here, yeah, we can see this 872,187 matches our solution. But there's a caveat to that. If we go up here to, no, it's right here. For the information on this problem, you can see it was first published on January 31st, 2003, sometime before time began. And you might be familiar with this concept of Moore's law. It hasn't been quite as much of a force in recent years, but for most of the early 2000s, it meant that every 18 months, roughly speaking, computing power would double. There are many caveats to this statement, but roughly speaking, it's a decent rule of thumb. And what that means is that computers today are probably several thousand times more powerful than computers at the time that this problem was posted. And so while a half-second running time is just fine on my workstation, if we tried to run this 18 years ago, this would probably take a lot longer. So let's look at some ways we could optimize our solution. Roughly speaking, so as I mentioned, there are two different approaches to optimization that I'm going to show you. The first is that we're going to optimize particular operations that are especially expensive in our solution. Obviously, this depends on the particular processor, the particular architecture that you're running on, but there are some good rules of thumb here. In particular, floating point operations tend to be very expensive, and if possible, it's better to use integer operations when doing arithmetic. Division is usually more expensive than multiplication, which is more expensive than addition. Also, memory operations, allocating memory, freeing memory, and copying memory are some of the most expensive operations. And so if you can minimize those, that's a good way of making your program faster. So that's going to be our next effort here. So the idea is that we're doing a lot of string operations here with our first solution. It would be nice if we could avoid those, because behind the scenes, the string class is doing a lot of memory allocations, maybe moving memory around. But we can avoid all that by just doing arithmetic operations to determine whether our number is a palindrome or not. Okay, so let's implement a new version of Is Palindrome. And this one is going to take both our an integer rather than a string, and then also a base. And the idea is that we want to find the exponent of the base, which corresponds to the most significant digit in our number. So if you imagine the number 2,345, in that case, the most significant number is the 2, and we can determine that that's the most significant digit because if we divide by 1,000, we get a non-zero value, that is 2. But if we divide by 10,000, then and ignore the remainder, then we just get 0. And so we know that 1,000 in that case would correspond to the position of the most significant digit. So that's going to be the first thing that we do. And I'm gonna create two different variables here, call them left power and right power. And the idea is we're going to have one that corresponds to the more significant digit that we're looking at, and the other corresponding to the less significant digit. And we'll repeatedly divide the one by the base and multiply the other by the base until we reach the center of our number. Okay, so we're going to start off with the left power, which is the more significant of the two. It's going to be equal to 1. And there's a point of caution here where we could repeatedly multiply left power by the base until it exceeds n, and then divide by the base. But if we have a 9-digit number, we can run into problems with overflow because you can't represent a 10-digit number as a 32-bit integer. And so instead, what we're going to do is we're going to have a temporary variable which is going to be initialized to n. And then we'll say while n is greater than 0, or while n, we'll say plus plus, or excuse me, yes, plus plus left power times equals base, and n divided by equals base. Now we have to be a bit cautious here because in the base case here, if n is a 1-digit number, then we will start off by, this is actually not entirely correct. We need to initialize temp by dividing n by the base. And that's because in the base case, we want n to already be 0 and left power to be 1. If we have a single-digit number, we don't even enter the loop here. Okay. So after this, we've got our left power, which is corresponds to the most significant digit or bit. And then we're going to say right power is equal to 1, right power, which is the least significant digit or bit. And then we're going to say while left power is greater than right power. And then we'll say if n divided by left power mod base is not equal to n divided by right power mod base, return false. So this is just extracting the digit which or bit which corresponds to the more significant power and the digit or bit which corresponds to the less significant power. Okay, and then we will say right power divided by equals base. Excuse me. Left power divided by equals base. Right power times equals base. And then return true. Okay, so now let's try solver, solver 2. And this is going to be very similar to our solver 1 function up here. Let's remove. So they don't actually make that much of a difference in this case, but just to make sure we're making a fair comparison here, let's remove those printf statements. Okay. All right. Let's see. So we don't need to do these string conversions now. And now we just say n comma 10 and n comma 2. So this will check using the code we just wrote to see is it a palindrome in base 10 and is it a palindrome in base 2. And we'll switch main to use our new solver. So you'll note again that our previous solution took about half a second. Our new solution is not even correct. Oh, I see. I've let an extra space sneak in here. Okay, so you can see that this solution is not correct. That's interesting. We can actually get a little bit of a hint. Let's do a quick sanity check here. I have a suspicion. Okay, yeah. It just thinks every single number is a palindrome. What? There we go. Okay, so apparently oh, I see. This is actually a good argument for making these constant, because that would have caught that mistake immediately. Okay, there we go. Now you can see our solution is working correctly, and we get the solution as expected. Let me again remove the extra printf there. Okay, so before our solution was taking roughly half a second, you can see now that it's taking more like 3/100ths of a second. Much better. Okay, so now we can look at the other way that we might optimize our solution, which is rather than using better operations which are more efficient on our particular processor or architecture, is to use a better algorithm. And this is kind of the point of computer science and the analysis of algorithms, is that certain algorithms scale better than others. And in particular with this algorithm, if we're trying to search the first million integers to see which are palindromes, our approach so far has been to try every single integer. But of course, that's really not very efficient because, for example, let's just create our solver 3. Put some notes here. Note, once we consider 1, 2, 3, 4, 0, 0, 0, we can skip to 1, 2, 3, 4, 3, 2, 1. So that is, we don't need to try 1, 2, 3, 4, 0, 0, 1, 1, 2, 3, 4, 0, 0, 2, etc. We know that none of those are palindromes. If we're looking at a 7-digit number that starts 1, 2, 3, 4, we know that there's only one 7-digit number that's a palindrome that starts off 1, 2, 3, 4, and that's 1, 2, 3, 4, 3, 2, 1. And so rather than try all million possibilities or all n possibilities, we can try just 1,000 possibilities. That is the square root of n rather than n itself. And in fact, for this approach, we're going to go back to using a string-based approach. Okay. uint32tn. I'm going to go from n equals 1 all the way up to n less than 1,000. Or we can say it a different way, n times n less than 1 million. I don't think we want to do it that way. We'll do n less than 1,000. Okay, so now we need a way of making a palindrome when we're given the left half of the palindrome. And one thing to consider is that there's a corner case here we need to be sure to take into account, which is whether the palindrome has an odd or even length. That is the center digit repeated or not? So we just have to be sure to take that into account. All right, so we'll say Uint32T make palindrome and this is going to say std string to call left. Yes. Equals std to string n. And then we're going to copy that. So we'll say std string right equals left. And then we actually need a separate variable here, has odd length. And we're going to say if has odd length, right dot pop back. That is, discard the last element of the string. And then we'll just say std reverse right dot begin, right dot end, and left dot push or append right. And then we can just say return a to I left dot cster. So that is, we're just taking the left side, copying it, flipping it, and appending the two, possibly removing that center digit as necessary. Okay. So now we're going to say, actually, let's do this way. Let's say odd. Say for odd equals 0, odd is less than 2, plus plus odd. Okay. And then we'll say so let's call this left also, just to distinguish from the full palindrome. And we'll say uint32t n is equal to make palindrome left comma odd. And then we'll say std string is binary is equal to to binary string n. And then we'll say if is palindrome binary sum plus equals n. Okay, so let's see how our new solver does. course, it has some issues. UInt32T is what we want. All right. Looks like the correct answer. Let's see how the performance is. All right, so you can see it takes 0 time. It might be worth briefly explaining the distinction between RIL, user, and sys here. RIL is the wall clock time. That is if you had a stopwatch that you could exactly start when the program started and stop it when the program stopped. That would be the RIL time. User is the total CPU time taken by the user space part of the program. That's the number that we mostly care about. And then the system time is the time used by the kernel, the total CPU time used by the kernel by our program. I'm assuming that the difference in this case is that it takes a certain amount of time just to launch the program. And that's probably accounts for the difference there. In any case, it's kind of hard to tell how much better, if at all, this program is than solver number 2. One way we can make the difference more apparent is if we ramp this up. So if we add another 0 on here, that will be, instead of searching for solutions less than 1 million, this will be finding all solutions less than 100 million. And so let's see how it does. Actually, let's first switch back to, let's look at how solver 2 does in that case first. So we have to add 2 zeros here, ramp that up to 100 million, make. Okay, so it takes roughly 5 seconds. And so now let's see how solver number 3 does. Bam, 0.016 seconds. That is our new solution, solver number 3, is several hundred times faster than our solution number 2. And that's because solution number 3, even though it's using less, remember, we went back to using strings for that solution. So it's technically, in terms of the operations, it's using less efficient than solver number 2, but it's using a better algorithm. And so that more than makes up for the difference. And in fact, if we were to continue to increase our search size, the difference would only continue to grow because solver number 3 has an algorithm which scales better. So I hope you found that interesting and informative. If so, then please join me for problem number 37, which we'll tackle in the next video.